Welcome. Simple harmonic motion where we focus our spring system. Here our focus is on the spring systems only. Now problem number 10. Let's solve the problem number 10. A vertical spring with spring stiffness constant 305 Newton per meter oscillates with an amplitude of 8.0 centimeter when 0.235 kilogram hangs from it. The mass passes through the equilibrium point with positive velocity at t equals 0. This is a drawing of the situation. Both equation describes this motion as a function of time. At what times will the spring be longest and shortest? Since the mass here in our program, see, the mass here has 0 displacement and a positive velocity as t equals 0. The equation will be a sine function, because at time t equals 0, the velocity equals 0 and the displacement is 0. A positive velocity at t equals 0. Now the amplitude is all given because it is a maximum displacement. See the maximum displacement here. The maximum displacement here. This is the amplitude. 10. The drawing of the situation first. Now we are asked to find the amplitude. We know that the amplitude is the maximum displacement. Is maximum displacement. Now the amplitude equal A0. Sorry, here we are given 28.0 centimeter, which is expressed in meter like this. Meter. Now what equation describes this motion as a function of time? Since the mass has a 0 displacement and a positive velocity at time t equals 0, the equation is a sine function like this. Our equation x as a function of t is a sine function. Why? Because, as already mentioned, the displacement equals 0. Now let's find this omega. Omega equal the angular frequency equal the stiffness over mass. The stiffness, let me see, problem. The stiffness, yes, the spring constant is given here. The spring constant, yes. Depressing, we find this angular frequency, omega, spring constant over mass root, we find 3.6026 radian. It is radian per second. Now, having this angular frequency, what equation describes this motion as a function of time? It's time to solve for A. This. Write equation like this. The displacement in a function of time, as a function of time. Angular frequency T. We have already amplitude, meter, sine, angular frequency, rad per second, T. This is a required equation, the required equation. This equation that describes the motion. B. At what time will the spring be longest and shortest? B. At what times? B. Times at which the spring will be longest and shortest. We have first of all to draw, show that this is a required drawing to solve the part B of our problem. Now let's show by analogy here. Now from here up to this equilibrium position here, see here, this is a half, a quarter the period. This half period. Back to the equilibrium position here. 1.5 period. Here to the initial position period. See here, to understand this, see the solving of the problem number 1. We encountered the same problem. Now in our graph here, this from here up to here, this is a quarter period. Here half period. Here at this point we have no, let me show you. We have 3/4 period, and here I have a period. See, by analogy here, let me show you. This a quarter period here, at this point half period, back to this point 3/4 period, to the initial position period. See, like this. See here, like this. Now you see here I have the maximum. You see here I have minimum, maximum. At time t equal 1/t, I have the longest position. See, and here, yes, and here, see here, I have also at time t equal period, I have again the longest displacement. Now let's write t maximum equal quarter period plus n period. You see, when you have a period, we have the longest displacement here, and on this quarter, you see. Now we express the idea like this, where n is 0, 1, 2. See, also in our problem, in our problem number 10, we also asked to find times at which we have the shortest spring displacement. You see, shortest and longest. You see, here I have the longest, here I have the shortest. Longest, shortest. See, now the shortest, look, the shortest see, here I have the shortest, here I have shortest is quarter, half, 3/4. I have the shortest displacement. It's y for the shortest times at which our spring will be shortest, minimum, here is minimum, here is max. Yes, we write 3/4 period plus n t, where n equal 0, 1, 2, and so forth. I have already my period. I already have my period. The period big T equal 2 pi over omega. Find 2 pi over omega, yes, omega here. Find 3, 6, 0, 6. Using calculator, I find 1, 7, 4, 4. Second, round off to get 1, 7, 4 second. Now, having this period, we will use this period to find the times. Let me come back in our problem. At what times will the spring be longest and shortest? Times at which the spring will be shortest, will be longest, are given by this relation, this question. Writing T will be longest, the string will be longest when I have a period over 4. Period, yes. 0.174 is a period, yes. 0 period equal 0 0.174 over 4 plus n 0.174, which is equal to 0.305 plus n 7. This is times at which our spring will be longest, will be stretched. Now, at this time, our spring will be shortest, meaning that period I have already the period big tail. Now at this time, three quarter times the period 0.174 second plus n 0.174 second we have 0.305 plus 0.7 second here there is a mistake here. Doing this using a calculator, you find here. Let me show you. You will find 0.435 seconds. Now the problem 10 part B is solved. It was the longest one because we included the graphs for more understandings. Yes, thank you for watching. See you in problem 11. Thank you for watching.